Let's do a little review. Chapter 13, Chemical Equilibrium. So I got 1, 2. All right, number 1. Consider the following equilibrium. All right, let's see. We've got H2 gas plus I2 solid is in equilibrium with this gas. Okay. All right, which of the following statements about the equilibrium is false? All right. Let's see. We're going down to E. All right, first one. If the system is heated, the right side is favored. We can't tell because we don't know if this reaction is endothermic or exothermic. If we were forced to choose, it would probably be exothermic, but we don't know. So we can't say anything definitive about it in terms of the heat. How about B? So I'm going to say that's a false statement. Oh, hold on a second. That's a question mark. It could be true. B, this is a heterogeneous equilibrium. Well, that's true. Gas is solids. That means heterogeneous. If the pressure on the system is increased by changing the volume, the left side is favored. So what happens if we change the volume? This has no impact on it at all. Only the number of gas molecules. So that's 1 mole. This is 2 moles. So if we increase the pressure, then it's going to try to reduce the number of moles of gas. So it should go this direction. Is that what that statement says? Left side is favored? Yeah, that's true. Okay. Adding more hydrogen increases the equilibrium constant. That's why they call it a constant, right? It doesn't matter what you do to the amounts. You don't change the constant unless you change the temperature. We didn't do that. So, and the last one, removing HI as it forces the equilibrium to the right. That's true. We remove this, shifts it that way. Okay. This is a case where pick the best answer. Since we don't know for sure about this one, the best answer is D. Okay. If there had been a choice, say 2 of the above, then I might have to give you that one. If you say that A is true and D is true, then 2 of the above might be true. And I'd give you that one. But if you put D instead, I'd have to give you that one too. Because A, it probably is. No, that's not going to be right. If the system is heated and it's exothermic, it'll go to the other direction. Right? If we put heat on the product side and we increase that factor, it's going to the left. All right, so this is a bad question. After all that trouble, I figured that this one is not a good question. Number 2. We ought to have some statement in there in terms of exothermic or endothermic. All right, number 2. Which of the following is true for a system whose equilibrium constant is relatively small? All right, so if K is much, much less than 0, what does that say? That says that the reactants are favored. It doesn't produce much product. We're saying that the reactants are favored at equilibrium. Okay. Does equilibrium say anything about how long it takes to reach equilibrium? No, that's kinetics, right? A and B can't be true. So C and D, it's either left or right. Equilibrium lies to the left in terms of the constant. So that's why C would be true. Equilibrium lies to the left in this case, right? And if the K were a lot bigger than zero, very large, equilibrium would be favored for the products. It's really that simple. All right, how about number 3? Scientists like simple. Complex gives us headaches. For this equilibrium system, let's see. All right, let's put the whole thing up here. CO2 and hydrogen. Is in equilibrium with carbon monoxide, yeah, and water. Let's see, is that going to be a gas too? Yeah, must be elevated temperature. Okay. This is endothermic, delta H. With 2 kilojoules. All right. So K in this case equals 1.6 at 1260 K. Okay, I'd say that's an elevated temperature. K equals 1.6. Let's see, are we going to need to do any calculations? If 0.15 moles CO2, hydrogen, carbon monoxide, and H2, all of them are at that concentration, we're placed in a 1 liter vessel, and the system comes to equilibrium. All right, we're going to have to determine which way this equilibrium has to shift. So that means we've got to calculate Q. K then is going to be carbon monoxide. These are all gases, so we have to include every term over CO2 and H2. So the Q is just going to be those values as we're given. And each one is 0.15, isn't it? 0.15, 0.15. This should be easy to calculate. Okay. Actually, that's the number of moles. The molarity is per liter, right? Since it's 1 liter, then that's also molarity. Okay, did I throw anybody on that one? It's 0.15 moles in a liter container. So this is molarity also. That value is equal to 1. Okay, so if the value is equal to 1 and K is 1.6, which way is this thing going to shift? Right? If this is smaller than that, Q is smaller than K, that means the numerator is too small and the denominator is too big. So if the denominator is too big, we're going this way. We're shifting to the left. Okay, which one of these statements satisfies the conditions? Oh, temperature also. Right? If this is endothermic, this delta H is on this side. So if it shifts that way, temperature is going to increase, right? Temperature increases. So let's see. That means D and E is only possibilities. D and E for the temperature increase. right? So we have to choose between the two. The mass of CO2 would increase or decrease. The mass of CO2 would increase. Is that D? Yeah, that's D. So D is the answer. In order to get to the understanding, right? In order to predict the movement, we had to calculate Q. Okay. That's the only way we can tell which way the system is going to move at equilibrium.
The paper says it's B.
B, the temperature would decrease.
I thought you said because the denominator would be too big, it would shift to the left. But the denominator is not bigger than K.
Oh, wait a minute.
Yeah, you got me all confused.
Hold on. Yeah, I'm probably confusing myself. If this is smaller than K, then this is too small and that's too big, right? Oh, yeah, it goes the other direction. I'm sorry. Yeah, this is the denominator. This is too small, moves that way. All right. Strike that. Temperature would decrease. So it's A or B for the temperature to decrease. That's the problem. I flip these things in my head.
So hold on, what you told us originally, if the denominator is too big, it shift to the left. So if the denominator is too big, would it shift to the right?
Actually, in this case, the denominator is too small because it's product. This is too small, makes this value smaller than that. So if this is too small, it has to go that direction. Yeah. I hope you're writing in pencil. Okay, so we have to choose between A and B. Both temperature decreased. The mass of CO2 would increase or decrease. If it's going that way, CO2 would decrease. Okay. So second time's a charm, I guess. You still have to calculate Q in order to answer the question. All right, let's try. Okay, 4, 5, and 6 are based upon this equation and the K that's given. Okay, so if we have let's see, 4, 5, and 6, and it's all based upon this hypothetical 2A is a gas in equilibrium with 2B and C. And C. Okay. So number 4 says addition of chemical B to an equilibrium mixture of above will what? If we increase this one, we're going to increase, it's going to shift this way. We're going to increase A and decrease C. Okay, A increase. It doesn't say anything. Well, C doesn't increase, C decreases. So A would be the best answer for this. Okay. Let's see, at a higher temperature, let's see, we're given a K value, 1.6 times 10 to the 4th. All right, are we told anything about at a higher temperature, K is 1.8 times 10 to the minus 5. So if we increase the temperature, now the K becomes 1.8 times 10 to the minus 5. All right. So if we increase the temperature, what is that doing? Increasing the temperature decreases the product and increases the reactants. Right? How can we do that? The only way to do that is if this is exothermic. Because if we increase the temperature, we have to shift this way to make this smaller. that means delta H has to be on this side. Okay, so now that we know that, we know it's exothermic. If we place the equilibrium mixture in an ice bath and lower the temperature, it's going to shift it back to the right. So in that case, we should see B increasing and C increasing. That's after we reach the new equilibrium at this high temperature. Then what would happen? Okay, right, we got a different equilibrium situation for B, for 5. So then if we put it in ice bath, we're going to shift the equilibrium to the right, and that would be B would increase. Okay. How about number 6? Raising the pressure by lowering the volume. If we increase the pressure, we have to look at the gas balance. We have 2 moles on this side and 3 moles on this side. So if we decrease the volume and increase the pressure, how's the system going to respond? It's going to try to produce fewer moles of gas. So increasing the pressure by decreasing the volume will shift it this way to the left. Right. So that would cause A to increase, B and C to decrease. Let's see, A to increase would be A. Okay. All right, let's skip down, let's say to this one. All right, number 8. We have a situation, if you add cobalt chloride to water, it's completely soluble. So the cobalt 2+ ion separates from, let's see. Okay, there's several steps that occur when you add cobalt 2 chloride to pure water. The cobalt 2, once it separates, then hydrates and sets up an equilibrium between 2 complex ions. One of them is hexaaqua cobalt 2. That's the one on the left, the pink one. And then that's at equilibrium with the tetrachloro cobalt 2, which is the blue on the right. So now we've got this equilibrium established. Let's see, I got something covered up here. Let me uncover it. Okay, there we go. The hydrated form then reacts with chloride ion to set up the equilibrium. Which statement below describes the change that the system will undergo if hydrochloric acid is added? Okay, if we add hydrochloric acid, what are we adding to the mixture? Chloride ions, right? Hydrogen ions are not in this equilibrium anywhere. So hydrogen ions could be considered as a spectator, right? If we add chloride, we're increasing the reactant side and pushing the equilibrium to the product side. So it should become more blue, right? A is a valid answer, right? More blue. Are any of the others valid, right? Well, it's not going to become blue and pink. How about equilibrium shifts to the right? Yeah, if it becomes more blue, it has to shift to the right, right? So both of those are true, A and C. That means 2 of these are true. So E is the answer. What would happen? I'm going to have to write the thing up here to say what if H2O 6 2+ chloride ions in equilibrium with. Yeah, that's right. Minus. And then water. Okay, what would happen if instead of adding chloride ions to this mixture, we added something like silver nitrate? Would that have an impact on the reaction? Silver nitrate. Silver nitrate is soluble. And what it does in water is it forms the silver ion and the nitrate ion. Now, which one of these, if any, is going to react with something in that mixture? Right? Nitrate not going to react with anything. That's a spectator. How about silver? Silver is going to react with chloride and make a solid. So what does that do to the reaction? It's a coupled reaction. It removes chloride ions, and the reaction then shifts to the left and becomes pink instead of blue. Okay? We're going to do several of those types of reactions Thursday in our Le Chatelier's lab. We're going to couple reactions. We have to couple reactions because it's easy to add components, right, and see the effect. Like in that the video where we had the iron complex turned brick red. Potassium cyanide and iron. But it's more difficult to remove a component from solution. Right? It can be done, and this is one way to do it. You couple a reaction that will remove some reactant or product, and then you see what the effect is. Right? In that case, we would see it turn pink, right, and shift to the left. It'd still be two of these, right? But it would be two different ones, not the same two as before. All right. That's number 8. Number 9. And 9 is based upon following equilibrium. Let's go ahead and write it up here. It's gas plus X2. All right. We don't know what X is. It's probably a halogen. X is usually used for halogens. Let's see, 2H2X gas. Right. Is that balanced? Yeah. And this is exothermic. Okay. Addition of X2 to the system. X2, if we add this to the system, right? What will happen? Right. Well, if we add to this one, we're going to decrease this one and increase that one plus heat. So it's going to get hotter, and we're going to deplete hydrogen gas and produce more H2X. So cause H2 to decrease? Yeah. X2 to decrease? No. Now, from the original amount of X2, it would decrease, but we're adding so much of it. So actually X2 is increased initially, and then it drops, but not to the same level it was. It's going to drop to a position where you reestablish equilibrium. So X2 actually goes up. H2 goes down, and C's not it because that one increases. Okay, So A is the best answer. Hydrogen gas decreases, excuse me. All right. Oh, while we're here, how about number 10? What if you add argon to the above equilibrium? All right, you've got 3 moles of gas on the left and 2 moles of gas on the right. Right? Add argon, you're going to increase the pressure. Will that have any effect on the equilibrium? No, because it's not part of the balanced equation. Argon is inert. It increases the pressure, yeah, but it doesn't change the number of impacts of any of the gases. It doesn't change how they will react to an increase in pressure. That only happens if you change the volume and the pressure. If you add an inert gas, it does nothing. Just means you need a stronger vessel. Okay, number 11. Which of the following statements is true? When 2 opposing processes are proceeding at identical rates, the system is at equilibrium. I couldn't say it better myself. That's the definition of equilibrium. That's true. E says none of the above, so that can't be E. And since that's the only choice, right, let's look at the others just for instructional purposes. Catalysts are an effective means of changing the position of an equilibrium. If you add a catalyst to the system, is it going to change the equilibrium? No. It'll be the same equilibrium position as it was before. It'll just get there faster. That's the only difference. It'll change both the forward and the reverse rate. Now, this is inorganic catalysts. If you have a biochemical reaction and you add an enzyme, it will change one of the directions most of the time. Change one of the directions. Right? So that's another issue. But inorganic catalysts, no, they don't play favorites. Forward and reverse reactions are both increased. So the catalyst has no effect on the equilibrium. Concentration, how about C? Concentration of the products equals that of the reactants is constant at equilibrium. Concentration doesn't have to be equal. Right? Depends on the reaction. Sometimes you have more product than you do reactant. So C is false. An endothermic reaction shifts toward reactants. Endothermic is heat term is on the reactant side. If you add heat to it, you're going to decrease the reactants and increase the products. So you don't shift toward reactants with an endothermic, you shift toward products. All right, let's go to number 12 now. 12, consider the reaction A plus B and C plus D. Well, let's do that. These are all gases. Okay. You have gases A, B, C, and D in equilibrium. Upon adding gas A, the value of K does what? It says they're at equilibrium, right? If we add gas A, it doesn't change K. Right? As long as the temperature is constant, there's no change in K. Right? K is a constant. Like we call it a constant for a reason. It doesn't change except with temperature. So D is the answer, right? That K doesn't change. All right. That's simple enough. How about, let's see, how about, okay, let's look at number 17. Ammonia is prepared industrially by the Haber-Bosch process. Might as well write it, I might need it. N2 gas plus H2 gas yields ammonia. And we need 2 here and 3 there. Okay. This is exothermic minus 92.2 kilojoules at 25 degrees. Oh, K at 25 degrees. Okay, so delta H is exothermic. Minus 92.2 kilojoules. And that means under standard conditions. So this is 25 degrees. And the K under these conditions is 4 times 10 to the 8th. Okay. So the equilibrium constant says the product is favored at that temperature. Okay, when the temperature of the reaction is increased to 500 degrees, which of the following is true? If we increase the temperature to 500 degrees, we go from 25 degrees to 500 degrees. See, right? Okay. Does the K change? Oh yeah, the K will definitely change. If this is exothermic, then we have the delta H on this side, and that doesn't change. The delta H, if it's exothermic at a low temperature, it's exothermic at a high temperature. So if we increase the temperature, we increase this value, that shifts everything to this side and makes the reactants much, much larger and makes the product a lot smaller. So K should decrease. Right? We add heat here, we get rid of that, right? That decreases, this increases, that causes the K value to decrease. In fact, it decreases into the negative powers of 10 quite a bit. All right, so to answer that question is, product formation at the new temperature is not favored. This K becomes very small. All right, now the thing about equilibrium is it doesn't say anything about how fast the reaction occurs. The product may be favored, but it might take 3 years for you to get there, right? And when Haber invented this process, he didn't have 3 years to wait for a little vessel to produce product. So he increased the temperature because he knew increasing the temperature would increase the kinetics. But he also knew that the reaction was exothermic. So if he increased the temperature, he was going to shift the equilibrium to the wrong side. Right? So I've told you this story before. So how did he deal with that? He increased the temperature to increase the rate. So how did he deal with the equilibrium? He forced the equilibrium to the right. Right? 2 ways. Used a catalyst, finely divided iron, to speed up the reaction in that direction, in both directions actually. And then he bled off the mixture, right? After a certain few minutes, he bled off the mixture and decreased the temperature. He decreased the temperature enough so that ammonia would become a liquid. But at that temperature, nitrogen and hydrogen were still gases because their boiling points are a lot lower. So he bled off this mixture, removed ammonia, and then sent it back in. So as he removed ammonia, which way was he shifting the reaction? That way. Yep. So that's how Haber dealt with it. And supplied Germany with all the ammonia they needed to make gunpowder. And now we use his process to make fertilizer. We make ammonia, ammonium nitrate, potassium nitrate, urea. It all starts with that ammonia. All right, so did I give it? Yeah, the answer. C, the product formation is not favored as the temperature is raised. Okay, number 20. Let's see. Mercury 2 oxide solid is decomposed to mercury and oxygen. Okay. 20. So let's see, our reaction is this solid produces this liquid plus this gas. And let's see, that's 2 and that's 2, and that's good. Okay, and the delta H is 43.4. That's a positive value. Kilocalories per mole. Right, we haven't talked about calories. That's the way, in fact, when I was a chemistry student, calories was the norm. That's what we used. You know what a calorie is? Food calorie is a kilocalorie. A calorie in chemistry is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. That's a calorie. All right. That's just interesting information. The mass of the mercury 2 oxide in the bulb could be increased by, okay, we want to increase this right here. That's our objective. Increase that amount. So how do we do that? At equilibrium. Well, we can add oxygen, right? What if we added mercury? What is the equilibrium constant calculation for this reaction? That's it. Right? So if you added mercury, you would not affect the equilibrium. It's not part of the equilibrium expression. Right? You'd have to add oxygen in order to increase this one right here. So removing some mercury would have no effect. Reducing the volume of the bulb, aha. If we reduce the volume, we put a squeeze on it, it's going to decrease the moles of gas in order to alleviate that pressure. So that would definitely shift it to the left. Oh yeah. Right. Adding more mercury, increasing the temperature will go the wrong direction because this is endothermic. Increase the temperature, you go the wrong way. Remove some oxygen, now that'd go the wrong way also. Right, so really the only one in here is reduce the volume. Reduce the volume, which increases the pressure, and you will shift to the left and produce mercury 2 oxide, more mercury 2 oxide in the bulb. How about number 21? Okay, don't get on time. Okay. 21. At 500 K, 1 mole of gaseous ONCl is placed in 1 liter container. At equilibrium, it's 5.3% dissociated according to the equation shown here. All right, so our equation is, and those are all gases. We have 2 ONCl gas, just to be thorough. And it's in equilibrium with nitrogen monoxide and is it chlorine? Yeah, chlorine. Yes. Okay. Determine the equilibrium constant. The temperature, I mean, if you're going to conduct the experiment, you'd need the temperature, but to do the calculation, you don't need the temperature. Right? We're given 5.3 dissociated according to the equation below. Okay, so if we set up our ice table, right? These are all gases, so they're going to be part of the equilibrium. And let's equilibrium constant, yes. Okay, so we need to know NO squared and chlorine first power is ONCL squared. We need values for those. So we got to have this one, and this one. All right, we're told that at equilibrium, that compound is 5.3% dissociated. So how did it get there? Well, 1 mole of gas is placed in a 1 liter cylinder. So we have 1 molar here, and we have nothing here. That's our initial condition, right? 1 mole of that gas in a 1 liter gives you 1 molar. All right, so we know it's going to shift that way. We're going to lose some here. We're going to gain some here, right? If we make this one X, then this one is 2X, right? Stoichiometry. And this one is minus 2X. Okay. But we're also told that this is 5.3% dissociated. That is 5.3% of that ended up over there. So if we start off with 1 molar, what's 5.3% of 1 molar? Because that's what we end up with over here. Since this is 2 and that's 2, then the loss of this one, the loss of 5.3% of 1 molar is going to show up here as plus 5.3% of 1 molar. Okay, and this is going to be half of that. Because it's 2 to 1. All right, so we actually have values in here. We don't need to do the X. Okay, so what's this? What's 5.3% of 1 molar? Use the decimal equivalent. Right? What is 5.3%? 5.3 parts per 100. Divide 5.3 by 100. How do we do that? 5.3 divided by 100. 1, 2, right here. 0.053. So this is minus 0.053 molar. That's how much it lost. This is plus 0.05 molar. And this is 0.053 divided by 2 molar. Okay? Everybody with me so far? All right. So what's 1 minus 0.053? That's a toughie. That's 0.947 molar. That's what's left of this. And this one is, of course, 0.053. And this one is 0.053 divided by 2, which is 0.265 molar. Okay, now we got values. We can plug them in here, find out what the constant is. So NO is 0.053, 0.053 squared. Chlorine is 0.2, oops. No, it's 0.027. Yeah, 0.027. There we go. My mistake. Didn't pay attention to my decimal point. And then this one is 947, 0 point. That's squared also. Okay. Now we have it set up. We just crunch some numbers. 0.053. Let's square that. And then 0.027 times that. And divide by 0.947 squared first. And divide by it. So I get 8.2 significant figures. 8.5 times 10 to the minus 5. And close enough. All right, pick the best answer. 8.3. Maybe I made a mistake in calculation. It was a rounding error. I'm sure of it. Okay. Everybody follow the logic, right? In case I change parameters. Okay. That's 21. And 22. Let's see. 22. That there we go. Let's see. Calcium carbonate is decomposed at 800 degrees to produce calcium oxide and carbon dioxide. That's how we make concrete. Just grind up limestone, send it through a big kiln that's heated to 800 degrees, and you end up with calcium oxide. Right? That's known as not quicklime. That's lime. No, that is quicklime. Excuse me. Calcium oxide is quicklime. Calcium hydroxide is slaked lime. And calcium carbonate is limestone. Okay, back to the problem. What's the question? What percent of calcium carbonate will react to reach equilibrium? All right, so let's put what we know up here on the board. We're going to take calcium carbonate, solid, and we're going to heat it, produce calcium oxide solid plus carbon dioxide gas. Right? Okay. The KP equals 1.16. 1.16. What does that mean? Like, let's see. I don't want to encroach over there too far. So what that means is that's a solid, that's a solid. This just means KP is equal to the partial pressure, or the total pressure, actually, of CO2. That's the only term in our equilibrium. So if we have 31.3 gram sample of calcium carbonate, put it in a 10-liter container and heat it to 800 degrees. So we're starting off with 31.3 grams. And we put it in a 10-liter container. And we heat it to 800 degrees. Temperature. 800 degrees C, right? Yeah. Okay, what percent of it decomposes? Well, excuse me. At equilibrium, this is a sealed container. At equilibrium, you're going to have a 1.16 atmosphere here. There we go. 1.16 atmospheres is that carbon dioxide, because this is the only term in the equilibrium. So that 1.16 atmospheres is pressure at 800 degrees C, in case we need K, 3710, okay? And pressure, temperature, this is unknown, number of moles. How about the volume? The volume is 10 liters. Does that look familiar? We can use the ideal gas equation to find out how many moles of that is produced. Right? Okay. So PV equals nRT and solve for N. That's PV over RT. Okay, so pressure is 1.16 atmospheres. Volume is 10 liters. R is, anybody remember? No, okay. 0.08206 liter atmospheres per mole K. And the temperature is 1073. Okay. So the number of moles of CO2 produced is what? 1.16 times 10 divided by 0.08206. Oops, start over. And 1073. Okay, so I get 0.1317 moles. Okay, that's how many moles of CO2. Where did that come from? That came from here, and the stoichiometry is 1 to 1. So that means we lost 0.1317 moles of calcium carbonate. Let's go back to the question. What percent of calcium carbonate will react to reach equilibrium? All right, so if that's the number of moles that reacted, we could either convert this to moles or we could convert this to grams. Probably be better to convert that to grams. So we want to multiply this where we have moles on the bottom, grams on the top. Right. So what's the molar mass of calcium carbonate? Well, let's see, calcium is about 40.08 grams per mole for calcium. Carbon is 12.01. 3 times 16 for oxygen is 48. So add them together. Let's see, 1, 5, 6, 8, 9, 10. 100.09, is that right? 10, 4, 5, 6, yep, 100.09. So we multiply that times this value. And I get 13.19 grams decomposed. So what's the percent? Right, what percent of calcium carbonate react? Well, all we need is 13.19 divided by 31.3 times 100. 1.3 divided times. I get 3 significant figures, 4.21%. Right? Oops. Decimal place in the wrong. Hate that. 42.1%. Right, 4% didn't make any sense, right? 13 is about 3 times 13 will be this. Right. 4% is definitely not that. Questions, problems with that one? It's just, you have to be methodical about it. I think the trick is recognizing that this right here is the only factor. So if we know Kp, we know the equilibrium pressure of carbon dioxide. And that is how we jump on our horse and ride to the end. Okay. 22, who's next? 24. Okay. It's not in the way of anything. Number 24. What are we doing? 10 o'clock? Check, be sure. Yeah. 24. I think that was wearing out. Nitrogen gas reacts with hydrogen to form ammonia. All right, here we go, Haber again. At 200 degrees in a closed container, 1 atmosphere of nitrogen gas is mixed with 2 atmospheres of hydrogen gas. At equilibrium, the total pressure is 2.2 atmospheres. What's the partial pressure of hydrogen gas at equilibrium? All right. Let's see. Let's write the balanced equation first. nitrogen gas plus hydrogen gas is in equilibrium with ammonia. Yes. So it'll be 2, this is 3. And what are we given? At 200 degrees, right? Okay, temperature equals 200 degrees C. In a closed container, 1 atmosphere of nitrogen is mixed with 2 atmospheres of hydrogen. 1 atmosphere, this is initial conditions. 1 atmosphere is mixed with 2 atmospheres. So, no, only 1 0. And there's nothing there. All right, so since we're working in partial pressures, we actually don't need the volume of the container, and we're not given the volume. Okay, at equilibrium, the total pressure is 2.2 atmospheres. So at equilibrium, the total of these values is 2.2 atmospheres. Okay, that's the total pressure. What's the partial pressure of hydrogen gas at equilibrium? We want to know what this one is. So we know which way the equilibrium is going to move, right? We know it's going to go that way. So that means we're gonna lose some of this, and we're gonna lose 3 of those, and we're gonna gain 2 of those. Okay? So far? All right, so what does that mean at equilibrium? We have 1 minus x, we have 2 minus 3x, and we have 2x. Okay? So if we add these together, what do we get? Well, let's see. Let's add up the numbers. 1 plus 2 plus 2. No, not 2. 1 plus 2 is 3. That's 3. And then let's add up the x's. There's a minus x and a minus, that's minus 4x, and a plus 2x is a minus 2x equals 2.2 atmospheres. Look at that. We got an equation in one unknown. All right, so what's x? Well, let's see. Minus 2x is equal to 3, 2.2 minus 3, which is 0.8. 0.8 minus. So throw out the minuses because the minus on both sides, and x is equal to 0.4 atmospheres. Okay, the question was, calculate the partial pressure of hydrogen gas. We want this one right here. This partial pressure is 2 minus 3x, right? That's for hydrogen gas. So if x is 0.4, then 2 minus 3 times 0.4 is equal to what? Well, this is 1.2, isn't it? 3 times 0.4. 2 minus 1.2, that's equal to 0.8 atmospheres. That's the partial pressure of hydrogen. Or B. Okay? Oh. I guess I didn't lose anybody. Okay. Oh, yeah, sure. Kayla's not showing up today, looks like. Maybe she had to work a double shift. Okay, that was 24. And let's scroll down to 25. The same equation. Right. Yeah. That's the Haber equation. I'm gonna just leave that up there. Just change the number and the values. All right, so 25, right? 25. Oops. Let's have to dig into my. Yeah, ready to go. There it is. Five. Okay. 2 moles of N2 and 4 moles of H2 are added to a 1 liter container. Right. The equilibrium concentration of ammonia equals 0.55. The value of K for the formation of ammonia. Okay, so we just calculate K. All right, so we have initial conditions. What do we have initially? We have 2 moles of nitrogen in a 1 liter container. So that means 2 molar. And hydrogen is 4 moles in a 1 liter container. 4 molar. And nothing there. So what else do we know? We're also given the equilibrium concentration of ammonia is 0.55 moles per liter, molar. So the equilibrium concentration of ammonia is 0.55, 0.5 molar. Okay. We need to calculate K, which is going to be ammonia squared divided by nitrogen to the first power and hydrogen cubed. All right. How did that get there? What kind of change gave you that one? The change was plus 0.55 molar. Right? So how did it get there? Well, if that is 2, then this would be half of that. That was lost. Okay. How much hydrogen was lost? Well, it would be, if this is ammonia, right, and we do a conversion, then ammonia on the bottom and hydrogen on the top, then this is 3 and this is 2. Yeah, that's right. So this is going to be 3 halves of 0.55. Okay. Now we're going to say 2 minus 0.55 over 2, and this one is 4 minus 3 halves, 0.55. We just need to calculate those values and then put them in our expression. Let's see, 0.55 divided by 2. That's not right. There, that's better. 0.275. And then we'll subtract that from 2. This is 1.725 moles. That's what we have left of nitrogen. This one is going to be 3 halves of that value, which is 0.825 subtracted from 4. And that's 3.175. And then we got that one already. So now we just need to plug those values in. Right? Ammonia, 0.55 squared. And nitrogen is 1.725 to the first power. And hydrogen is 3.175 cubed. Okay, 0.55, let's square it. Okay, and then divide it by 1.725. And then 3.175. And cube that. And divide that into. And I get K equals 5, let's see. Actually, two significant figures. 10 to the minus 3. Okay, so C is our answer. Okay. I know that was a lot of work. 26. See what 26 has to say. No pictures? Okay. All right. Moving on. Six. All right. Given the equilibrium constants for the following reactions. Okay. What's the K for 2 copper plus oxygen yields 2 copper 2 oxide? Okay. Our target equation is that third equation. That's where we're headed. This is our target. Let's see. Copper solid. O2 gas 2CuO. Okay. And we're supposed to work it from, the first one is 4 copper plus O2 gas. It's in equilibrium with 2Cu2O solid. And that has an equilibrium constant of K1. The second one, I'm going to move it down a little bit in case I have to mess with that one. The second one is 2CuO solid yields Cu2O plus 1/2 of 2. And that's K2. All right. We've got to combine these two to make that one. So where's our, let's start with copper. Where's copper? Copper's here. We only need half of that copper, right? So we're going to say times the whole thing is 1/2. That gives us 2 here, 1/2 there, and 1 there. What does that do to the K? When you multiply a factor times your equation, that becomes the power of the equilibrium constant. So now our new equilibrium constant is K1 with a 1/2 power, right? Because we multiplied it by 1/2. It's a square root of K1. All right, that takes care of this one here. All right. How about copper oxide? Well, it's on the wrong side, isn't it? It needs to be on the other side. And we have 2 of them, so really we just need to flip it. So Cu2O solid plus 1/2 O2 yields 2 copper oxide solid. All right, so we're going to use this one and this one. This here, right here. That one is taken care of here. How about the oxygens? Well, we got a 1/2 an oxygen there and a 1/2 an oxygen there. That gives us a whole. Okay. And then this one, there's one of those here and one of those there. They cancel. But what did that do to the K value? If we flip the K, what does that do to this K now? The new K is the inverse. Right? We exchanged reactants for products. So now this one is 1 divided by K. Okay, so when we combine these two reactions to get that, what does that do for the K? When you combine reactions into your target, you multiply the Ks. So this is going to be K1, let's see, this is 2. K1 to the 1/2 times 1 over K2. All right, so which one looks like that one? Well, this is 1 over K, so we could also write it this way. Just put it in the denominator like it is here. There you go. So that's why E is the best answer. Okay, all right. Okay. That was 26 and 28. Exactly 1 mole of dinitrogen tetroxide is placed in an empty 1 liter container and is allowed to reach equilibrium described by this equation. So we've got this 4 is in equilibrium now with 2 and 2 gas. Yep. If at equilibrium N2O4 is 37% dissociated, what's the value of the equilibrium constant for this reaction? All right. 1 mole in 1 liter means that initially we're starting off with 1 molar. Nothing over here. At equilibrium, we're left with, let's see, we're used up 37%. So we've lost 0.37 molar, right? That's the decimal equivalent of 37% times 1. All right, so we lost that much. What do we gain over here? Well, it's 0.74 molar. Right? 0.74 molar is what we gain there. What do we have here? Well, let's see, subtract that from 1. Right, 0.63. Is that right? So we have our equilibrium values. We just need the expression. Right, for K equals NO2 squared and N2O4 to the first power. So that's equal to 0.74 squared divided by 0.63. There we go. Now it's just crunching numbers. Square that in 0.63 divide. I get 8.7. 8.7 times 10 to the minus 1, or is it in, it's in standard. So we move the decimal over, it's 0.87. That's your K value. Okay. Number 29. No, I don't. It'll make erasing a whole lot easier. Yeah. Next, 29. We didn't just do that one, did we? No, we hadn't done that one yet.
We just did 28.
Okay, thank you. 29. Consider this reaction. H2 plus I2 is in equilibrium with 2HI at a high temperature. All right, that's important because at a high temperature, not only is hydrogen gas, iodine is gas, and hydrogen iodide is also gas. They're all gases. That's important. We need to know that, otherwise we can't solve the problem. So the K is 44.8. K equals 44.8. And we'll build the equation if we need it. If an equimolar mixture of reactants gives the concentration of the product to be 0.5 molar at equilibrium, what's the equilibrium concentration of hydrogen? All right. So if the tendency is to go ahead and set up your ice table, which is fine. I'll do that. It says that the product equilibrium concentration is 0.5 molar. Molar. Okay. We started off with equal amounts of these two, right? We don't know what that is, but they're equal. Right? If we end up with 0.5 here, that means we had to have 0.5 there. Right? So that means we had to lose 0.25 here and 0.25 here. Okay. So it's natural to say, all right, this x minus 0.25. And this is x minus 0.25. But notice these values are still equal, right? Because that's 1 and that's 1. We ended up here equal. And the question is, what's this concentration? All right. One of the tricks for doing equilibrium calculations is if you set up an ice table, you want to try to make your unknown equal to the answer to the problem. The answer to the problem is that value. But these two are exactly equal. So I say, let's just do that. Right? We know what that is. We know what these are going to be. Then we can say K is equal to HI squared over, well, I'll complete it here. Like this and this and that. So now we put in our values. We know this one is 0.5 squared. We know this one is y squared. Y, I'm getting ahead of myself. This is y times y, which is y squared. So K is equal to, what's 0.5 squared? You do that in your head? 0.25? Yeah, 0.25. 0.25. And then this is y squared. You know what? Let's not do that. Here's why. This K is equal to 44.8, which is equal to 0.5 squared. And this is y squared, right? Y times y. Let's factor out that square. So now we got 0.5 over y, and we would square it, right? But we want to get rid of that square, so we take the square root of both sides. Now we have this side is the square root of 44.8. Okay? So what's y? We'll bring the y over here, like that. We leave the 0.5 over here, and we put the square root of 44.8 over here. Okay, everybody follow me? All right, so now the calculation is simpler than squaring that one. 0.5 enter, and then I'm going to 44.8, take square root up first and divide it. Okay, so y equals 7.2 significant figures times 10 to the minus 2. Molar. Okay. All righty. It's a little better. A lot better if I had time to clean the board first. And then squirt it down with W. All right, 29. Let's see. 30. Consider this equation. 2HF gas is in equilibrium with hydrogen and fluorine gas. Okay. And the K is 1 times 10 to the minus 2. Right. Given 1 mole of HF, 0.362 moles of hydrogen, 0.75 moles of F2 are mixed in a 5-liter flask, what's the reaction quotient? Okay. So all we need to know is the initial amounts in order to do the quotient. So I have 1 mole of HF. All of these are in a 5-liter flask. So the initial concentration here is 1 per 5 liters. Right? That's what, 0.2 molar? 1/5. And then 0.362 for hydrogen. 0.362 in 5 liters. Right, that's a liter and that's moles. Is equal to what? Just go ahead and calculate it now. 0.362 divided by 5 is 7.24 times 10 to the minus 2 molar. And then fluorine is 0.75. 0.75 per 5 liters. 0.75 divided by 5. That's 1.5. 0 times 10 to the minus 1. Okay, so we have our values in a non-equilibrium situation. What we need is Q. So Q is going to be concentration of hydrogen, concentration of fluorine, concentration of HF squared. We just need to put the values in there. All right, so hydrogen is 7.24 times 10 to the minus 2 molar. And fluorine is 1.5 times 10 to the minus 1 molar. And then HF is 0.2 squared. All right. So let me see. I've still got these two in my calculator. I'm going to multiply them. And then I'm going to say 0.2 squared and divide that into. And I get 0.272. Standard notation. Yeah, that's Q. Now, since we don't know what the K is, we can't say which way that's moving. But fortunately, that's not the question. 32. Right. Carbon disulfide and chlorine react to produce those compounds. Carbon tetrachloride, I know. Yeah, disulfur dichloride. Yeah. 2.14 moles of carbon disulfide and 5.85 moles of chlorine are placed in a 2-liter container. They come to equilibrium. Mixture is found to contain 0.62 moles of carbon tetrachloride. How many moles of chlorine are present at equilibrium? All right, so let's do our thinking on the board. CS2 plus 3Cl2 is in equilibrium with S2Cl2 and carbon tetrachloride. Okay. Initially, what do we have? 2.14 carbon disulfide in a 2-liter container. Yeah. 2.14 moles in a 2-liter container. That's our concentration. Chlorine, we're starting off with 5.85 moles in the same 2 liters. Okay. And we got nothing here, nothing here. So let's calculate what this value is. All right, 2 into that should be 1.07, right? Molar. And this one should be, let's see, can I do that in my head? 2.9 and round it off. Let's keep the decimal for rounding error. How about that? Yeah, that's right. Okay, so we have a change and we have an equilibrium. We're given something else. 0.62 moles of carbon tetrachloride in 2 liters at equilibrium. 0.620 moles per 2 liters. Right. So that's equal to 0.310 molar. Okay. Now, how did it get there? Well, we had to add that. Right. That means if there's 1 here, that means we had to lose 3 of these. 3 times 0.310 equals 0.930 molar is what we lost. And these are 1-to-1. So that means we lost 0.310 molar here. Now go back to a question. How many moles of chlorine are present at equilibrium? All right. Let's see. I don't think we need the equilibrium constant. We're given enough information. So what's left at equilibrium? We just take that one of this value, subtract it from that value. 2.925 and subtract 0.930. So I get 1.995 molar, or rounded. No, I did something. Did I do something wrong? I did something wrong. Anybody spot what I did wrong? We're starting off with 2.14 in 2 liters. That's right. We're starting off with 5.85 in 2 liters. That's right. And we're ending up over here with 0.62 moles in 2 liters. So that's right. That one's right. That one's right. That one's right. Must be in here. So we ended up with this molarity because we added this. This was the change, 0.310. If we get one of those, did I put the right? Yeah. If we ended up with one of these, we had to lose 3 of those. Right. Now, why does it say 3.99 moles? Oh, duh. Anybody see my mistake? The question is not what's the concentration. The question is how many moles? This is molar times 2 liters. Right? So 2 times 2 is 4, or 3.99. There you go. It helps to read the questions. Imagine that. All right. And scooch down to 33. See what time we got. Okay. Are we getting close?
Yeah.
Okay, good. At minus 80 Celsius, K for this reaction is 4.66 times 10 to the minus 8. We introduce 0.047 moles of N2O4 into a 1 liter vessel at minus 80 and let the equilibrium become established. Total pressure in the system at equilibrium will be. All right. So we're back to this. We looked at this one before. N2O4. Right? Yep. And this produces 2 NO2 gas. And actually, since we didn't change the temperature, that's irrelevant. But the K is given as
It's the 4.66, right?
Yes. Yeah, the K is 4.66 times 10 to the minus 8. Yep. So initially, we introduced 0.047 moles in 1 liter. So it's 0.047 molar into the container and let it come to equilibrium. All right. That K doesn't tell us. Maybe we don't need it. Hold on a second. That's 0. So change equilibrium. So we're gonna lose some of this, and we're gonna add that much. Right? It has to be molar. Yeah, it has to be molar. Because it doesn't make any sense otherwise, because these units are in molarity. And we're not told that this is pressure, so that has to be in molarity. Right? 0.047 minus X, and this is 2X. Right? So this is going to be 4.66 times 10 to the minus 8 is equal to 2X squared, right? And 0.047 minus X to the first power. Let's see. This is going to give us a quadratic, I think. Look, this value is so small, that X is going to be insignificant compared to this value. Because this is 4 to the minus 2, and that's 4 to the minus 8. So I think we can estimate this to be, let's go ahead and square that, 4X squared over 0.047. And that's equal to 4.66 times 10 to the minus 8. All right, so I'm going to multiply this one times that value. There times 0.047. And that's equal to 2.19 times 10 to the minus 9 is equal to 4X squared. So if we divide that by 4, by both sides by 4, I get 5.48 times 10 to the minus 10, and then x would be the square root of that value. Which would be 2.34 times 10 to the minus 5 molar. So x is, let's see, the concentration at equilibrium for this one. We need to know the number of moles, right? If x is that value, then 2x is 2 times 2.34 times 10 to the minus 5 molar. That gives us the number, well, actually that gives us the molarity. Right. Yeah, that's x. That's the molarity. Molarity times volume equals moles. So we need to multiply that times the volume. What's the volume? 1 liter, right? Times 1. Right, so 2 times that value is 4.68 times 10 to the minus 5 moles of NO2. How about this one? This would be 0.047 minus 2.34 times 10 to the minus 5. And that's the molarity of N2O4 times 1 for liters, and that's equal to the number of moles. So I need to switch this and change the sign, 0.047. So I get 4.70 times 10 to the minus 2 moles. Okay? So that's the total number of moles of N2O4, total number of moles of NO2. We're at 800 degrees. And we have a volume of, let's see, question was, oh, what's the total atmospheric pressure? So what we need is these values. Right? We're going to solve for this one. What's the volume? 1 liter, right? Number of moles we're going to calculate. Temperature is minus 80. Minus 80 plus 273. Right? 273. 80. That's 193. Okay. Number of moles is add these two together. So let's see, I need to add those together. So this is 4.70 times 10 to the minus 2 moles. Now we can solve for pressure. PV equals nRT. P equals nRT divided by V. So the number of moles would be 4.70 times 10 to the minus 2. R is 0.08206. Temperature is 193. And volume is 1 liter. Okay. So 0.08206. 193 divided by 1. So I get, let's see, that's in, yeah. So move it. Yeah, move it 1 to the left and I get 0.745 atmospheres. Close enough. Actually, if we round it 2 places, it's actually 0.74 because it's 0.7447. And if I can only have, yeah, 2 significant figures, so 0.74 is correct. That's B. There we go again. It's a lot of work just to get one piddling little answer. Number 34. So we didn't need the temperature after all. All right. 34, a sample of solid ammonium nitrate was placed in an evacuated container and then heated so it decomposed explosively. That sounds like fun. It made dinitrogen monoxide or nitrous oxide and water. Solid decomposed into two gases. At equilibrium, the total pressure in the container is found to be 2.63 atmospheres at a temperature of 500 degrees. Calculate Kp. All right. So 34 is based upon this equation. Ammonium nitrate and it decomposed to N2O gas and water. Gas. Okay. If we're going to calculate Kp, we need to know pressures. So Kp is going to be the partial pressure. That's a solid. So we're not even going to have a denominator. We're just going to have a numerator. Partial pressure of N2O times the partial pressure of H2O squared. Right? So let's see, at equilibrium, it doesn't say how much, just a solid sample. And the total pressure in the container was found to be 2.63 atmospheres. All right. So at equilibrium, the total pressure was 2.63 atmospheres. We need to find out what these two values are. Okay? Let's see how simple we can make this. How do we get here? This value plus that value. What is that value equal to in terms of Dalton's law of partial pressures? It's the combination of these two pressures. What's their stoichiometric ratio? If this is X, that's 2X. Right? So if this is X plus 2X, right, then what's X? Well, 3X is equal to 2.63. So X is equal to, let's see, 3 in that. Let's see if I can do that in my head. 0.8. 23, it'd be rounded off 8. Okay. So that means this one is 0.88, and this one is 2 times that. 176. Excuse me. 1.76. Let's see if that adds up. That's a little high. What if I want to avoid rounding errors. So 2.63 divided by 3. It's 0.877. Let's do this. 0.877. There we go. Then we won't get the rounding error. And then this one is going to be 2 times that. 1.753. There we go. So we got atmospheric pressure for these two. We just plug it into the formula, right? Kp equals partial pressure at 0.877 and then 2.6. Oops, Scott. Wait a minute. Yeah, that's right. 1.753 squared. So 0.877 and then 1.753, square that, and multiply. So I get 2.70. C. Okay. Let's see. How we doing? 36. Still got time. May not have time to talk about the lab though. If I don't get done. It's pretty much a cookbook lab anyway. At a certain temperature, K for this reaction, 2NO2 in, okay, they'll reverse that reaction now. And 2NO2 is in equilibrium with N2O4. These are both gases. Okay. Is the K for this is 7.5. Okay. So the product side is favored. If 2 moles of NO2 are placed in a 2-liter container, all right, so initially 2 moles of NO2 in a 2-liter container. So that means the concentration is 1 molar. It's 2 divided by 2. And that's 0. And permitted to react, calculate the concentration of N2O4 at equilibrium. All right. So our change and our equilibrium here. All right, so what's going to happen? It's going to go this way. So if we say we're going to add that much over here, that means we lost twice as much over here. So 1 minus 2x and x go into the final calculation. So K is 7.5 is equal to N2O4 times NO2 squared, which equals N2O4, which is x. And this is 1 minus 2x squared. And the question is still, what's the concentration of N2O4 at equilibrium? So we solve for x. We end up with a quadratic here. And what's worse is since this value is so large, that is going to be a substantial value there. So we have to calculate it based on the quadratic. All right, so let's expand the quadratic. What does this quadratic look like? If we square it, now we end up with 1 times 1 is 1. Minus 2x times minus 2x is plus 4x squared. Then 1 times 2x minus 2x and 1 times minus 2x is minus 2 times that is minus 4x. That's our expanded, our polynomial. 7.5. So let's take x and go through there, right? We need to do that. Did I do that right? That's x. Yeah. That's going to give us a cubic equation. I get the feeling I'm barking up the wrong tree. Let me be sure to save ourselves some time. It's that one. 7.5. Get the feeling it's should be easier than that. That's right. 1 molar. 2 moles and 2 liters. Okay. Get X. That's 2X. Hmm. Yeah, I don't see any way around it. Oh. Oh. And you guys just sat there, let me do this. You just sat there and let me do this. What is the K expression? N2O4 over NO2 squared. All right. N2O4 now is X in the numerator. And NO2 is 1 minus 2X squared in the denominator. Okay. So we still have to expand the polynomial, expand the squared. So that would be 1 and then minus 4X squared and then minus 4X plus 4X squared minus 2X. There we go. Now, this is all under X. Bring that to the other side. 7.5 times 1 is 7.5 minus 4 times 7.5. What's that? That's 30, isn't it? Yeah. That's minus, oops, already got a minus in there. Minus 30 X, and then 4X squared times that is plus 30 X squared equals X. Then we bring that X over here because when you solve a polynomial, everything's got to be on one side and zeros on the other. Okay, so bring the X over here. Now it's a minus X. That's 7.5 minus 31X plus 30X squared equals 0. Okay, the way I've written that is not the way you normally see a binomial equation, right? This comes first, then this second, and this is third. So we got to label them. This is our A, this is our B, and this is our C. Now we can use the quadratic equation. X is equal to minus B plus or minus square root of B squared minus 4AC all over 2A. Right. So minus B is minus 31. So it's a plus 31 plus or minus square root of B squared. So it's minus 31 squared minus 4 times A, which is 30, times C, which is 7.5. Okay, did I do that right? There's B. It's a minus, and this is 4A C, yes. Okay, now all over 2A. 2 times A, which is 30. Okay. So let's say, what is this right in here? 31 squared. All right. And then 4 times 30 is 120 times 7.5. And we're going to subtract that from this one. So that's 61. This inside here is 61. Take the square root of it. 7.81. So we got 31 plus or minus 7.81 divided by 2 times 3 is 60. Okay, so we have two possibilities. X can either be this one plus that one divided by 60. Do that first. 31, enter. 81 plus and 60 divide is 0.647, or now we subtract 31, enter, 7.81 minus divided by 60. Or it could be 0.387. Either one. Okay, which one makes sense? Well, let's see. If we say 0.647 here, what's 647 times 2 is greater than 1, isn't it? It's greater than 1, so it can't be that one. You'll end up with a negative number. So it's 0.387 or 0.39. Okay. That was fun. If you're a nut. The other option we have for solving these types of problems is to make that assumption and say that let X be 0 here, then solve it for X. We know that X is not going to be right. Then you go back in and put that X value that you solved in here and solve for that X until you get within 5%. That's successive approximations. And if we had a cubic or a quartic or anything that was worse than that, powers of 5, 6, 7, 8, 9, if we had a problem like that, then the successive approximations would be the only way to solve that problem. I mean, I've seen the cubic solution to an equation, and it's a nightmare. So I can only imagine what a quartic or a quintic would be. Let's see. Oh, we're done. We're done.